So welcome to another lecture. In this lecture, we'll be doing another SHM plus fluid mechanics problem. A uniform cylinder of length L and mass M having cross-sectional area A. So we have a uniform cylinder which has a length L and has a mass M, and the cross-sectional area is A. Is suspended with its length vertical from fixed point massless spring such that it is half submerged in a liquid of density rho at equilibrium position. So this is the first line. It is uh, half submerged in the liquid. So in the second line, they say when a cylinder is given small downward push, released starts oscillating with a small amplitude. See, the push which is given is a small downward push. There's a small amplitude. Force constant is given k. Find the frequency of oscillation of the cylinder. So this question is similar to another question which I had done. So this was the other question which I had done. Again, both of these are JEE questions. In this question, there was a sphere, and the sphere was doing an SHM, and we had to calculate the frequency. So in all these questions, the template is same. There is another kind of question which I'll be doing where there'll be angular displacement. So there'll be a rod like this, and then we will be given a small. This rod would be given a small displacement, and this rod will small angular displacement, and then there will be few condition, and this rod will oscillate like this, and then we'll have to find the frequency. So in all these questions, three lines are usually given. In the first line there is a equilibrium condition. In the second line, they mention what happens, and in the third case we have to find the frequency. So before I start this, there are few things I want to quickly cover, because these are the formulas I'll be using. So first thing that I need to convey is that mass is equal to density into volume. You understand this, density is equal to mass per unit volume. Critical thing which I need to make sure that you understand is that buoyant force by a fluid is equal to weight of the displaced fluid. So whatever be the buoyant force of the fluid, that is equal to the weight of the displaced fluid. Now weight of the displaced fluid is can be written as mass of the displaced fluid multiplied by g. G is acceleration due to gravity. Now, when we have to calculate the mass of the displaced fluid, remember that we have to take the density of the fluid and multiply that with the volume of the solid. What I mean by saying this is that in this question, whatever be the volume of this submerged part of the solid, this will be equal to the volume of the fluid displaced. I hope you are able to make this point. This point is very critical. Uh, Another formula we'll be using is that F is equal to minus kx. You understand this. This is the restoring force of the spring. Then from SHM, what I'll be using is that m d square x dt square would be equal to minus omega square mx. Usually you would have seen this equation in the form of d square x by dt square is equal to minus omega square x. This is the form usually you would have seen this. What I have done is I have multiplied both sides by m, so that this becomes a force equation. This would be basically the restoring force, and then this m would come on the right hand side also. So this is another equation I'll be using, because this will help me to calculate the omega. Once I have the omega is equal to 2 pi f, and finally f would be equal to 1 by 2 pi omega. So f is the frequency and omega is the angular velocity. So these are the formulas that you need to understand before you attempt question like these. And if there is any doubt, please let me know. I'll make a separate lecture, but I won't be discussing in detail any of these formulas now. Okay, now let's come to the question. The first is the equilibrium condition. The equilibrium condition, when we are doing the equilibrium condition, what we need to understand is that there is a weight which is in the downward direction. It is the weight of the cylinder. The weight would be given by, because m is the mass, g is acceleration due to gravity. This is simple. So this is the weight. I'm calculating the first. I'm calculating the equilibrium condition. Equilibrium condition. I'll imagine that the spring got stretched by an amount x naught. So this is the initial condition where the spring is in equilibrium. So I'll imagine that the spring has been stretched by x naught amount. So in the equilibrium condition, there will be a restoring force which will be in the upward direction. This would be equal to k multiplied by x naught. This would be the restoring force. This would be the restoring force. Then there will be a buoyant force. The buoyant force Fb, which will be due to the fluid. Now for calculating the buoyant force, as I have told you, I'll be using this formula. So rho F, rho is the density of the fluid multiplied by G. I have written it G rho. Now volume of the solid submerged. You always have to calculate the volume of the submerged part of the uh, of whatever solid you are putting in. Now because the volume of the cylinder can be given by the full cylinder volume can be given by L multiplied by A. L is the length and A is the area of cross section. So half the volume, because it is half struck, so half the volume would be equal to half LA. So that is why you see a half LA. That is why you see a half LA term here. So this will give us the point force. Very critical to understand. So this is the equilibrium condition, and in equilibrium condition, the equation therefore that we will be having is that kx naught plus half LA rho g is equal to mg. I hope this is clear. This is the equilibrium condition. I'll be using this uh, equilibrium condition shortly. Now, once I have given it a small displacement, I press it down, and let us assume that now the elongation is x. Now when the additional displacement that I'm giving is x, so x naught is the initial and x is a small additional displacement that I am giving. So due to that, the restoring force will increase from kx naught to kx naught plus x, because x is the additional amount. X is the additional amount that through which I am stretching the spring. So x is the additional amount. Then uh, due to this additional x, the buoyant force will also increase. Why the buoyant force? Uh, why the buoyant force will also increase? The buoyant force will increase because more part of the solid would be getting submerged. So for example, let me explain it here. So let us say initially, as we are aware that initially only half was submerged in water. Now when you press it, now more amount of volume would be in the fluid. So due to this additional volume, more amount of buoyant force would be created. So that is why the buoyant force will also increase. So if previously half L was submerged in water, now due to additional x, half L plus x will be submerged in water. So this is what I have written here, L by 2 plus x. So this is the additional amount, and due to this additional amount, you will have additional buoyant force. And if I subtract the restoring force of the spring, the buoyant force, both of these are pointing in the upward direction from the weight which is in the downward direction, this would be my restoring force. This would be the net restoring force which will be bringing the SHM into which will be bringing SHM. So, and what I'll do next is that I will manipulate this equation. I'll manipulate this equation and I'll write it like this. So mg part is here, minus kx naught part, this kx naught part, it is written here, and minus L by 2 into A rho g part. this is written here, minus xk, this xk, and minus a rho g. So I have manipulated the equation like this, that this part I have kept separate and this part separate. Why? Because if you see carefully, if you look carefully, I have this equation. So that is why this whole part becomes 0 and I am just left with minus k a rho g x. Now this is what I wanted to state, that this is the format in which a restoring force looks like. When you look at SHM, if you are able to reduce the equation in this form will tell you that this type of force would bring in a simple harmonic motion. Now we use this equation that we have discussed previously, md square x by dt square is equal to minus omega square mx. This is the equation that I used here. Then you compare these two, and finally you arrive at that omega square is equal to minus k a rho g upon m. So this is what this part and this part. You will be comparing these two parts and you will get omega square is equal to k a rho g m. The minus will get cancelled, and finally omega is equal to root k plus a rho g upon m, and this is omega is equal to 2 pi f, and finally you get f is equal to 1 upon 2 pi k plus a rho g upon m. Now I know k, I know area of cross section, I know rho, I know g, I know the mass. So this is the frequency of the uh, frequency of the uh, simple harmonic motion. So uh, these are interesting questions. See, this question was also this. I think this was asked in JEE 2004. This question, I think it's a 1990 JEE question. So these are fun equations. These are fun questions where you understand lot of concepts come together, and it's a good practice to do all these kind of questions. So I hope this was useful to you, and please like, share, and comment, and hope to see you in the next lecture too. So thanks a lot for watching, and best of luck.